Welcome to the Chemistry 151 Chapter 2 Section 2.4 lecture, where we're going to really explore what a chemical formula can do. There's a lot more that can be done from figuring out, for example, that sodium chloride is NaCl than you might have thought of before. In the way that people make things and the way that people analyze things, those formulas can be really helpful. So let's kind of investigate this and see what's going on. A formula actually has, like I said earlier, a lot of information for the chemist. And in this section, we're going to see how the formula will lead us to what's called the molar mass. We're going to see how Avogadro's number can help us. And there's a little funny flyer maybe you've seen before if you haven't. That's Avogadro's picture supposedly right there. And that weird number is Avogadro's number, but we'll talk about that. We'll see how these kind of things lead to what's called the percent composition. So if you want to know how much oxygen was in water, keep listening, we'll find it out. And then finally, we'll investigate what's called the empirical formula and molecular formula for a compound. And one of the ways that chemists get paid a lot is by figuring out what exactly is inside some substance. And to do those kind of things, you've got to know about the empirical formula and molecular formula. So this is a pretty important chapter. Let's check this out.
When magnesium metal burns, the product of the reaction has a greater mass than that of the original magnesium. John Dalton's atomic theory successfully explained this seemingly strange result.
The alkaline earth magnesium metal is actually fairly reactive with oxygen when you give it enough energy. And the really bright light comes off there, pretty interesting. And it makes magnesium oxide. Magnesium, a group 2A metal, is a fixed charge metal. We know it's always positive 2. And oxygen, non-metal, in group 6, 6 minus 8. Oxide, always negative 2. So MgO is made. Now on the bottom down there, you're seeing some little pictures. The one kind of in the middle at the bottom, that's pure magnesium, and the other one is magnesium oxide. The chemist has colored the oxygen atoms as red. Magnesium looks metallic, so you can see it's kind of 1 Mg for every 1 O. And ionic compounds, which is what you have when you have metals and nonmetals come together, they make those cool three-dimensional network things that are super strong. However, in this section, it might be kind of cool to know how much of the magnesium oxide is created if we have so many grams of magnesium. So let's say that you have 3 grams of magnesium and you're curious how much magnesium oxide you can make. The tools in this section will allow you to do those kind of procedures. Chemistry is a very quantitative science, all right? Quantity means you have to know how much of things that are around. So I just said 3 grams of magnesium. That would be a quantitative kind of analysis. And if we're going to do anything counting, we're going to need a counting unit, all right? As an example of this, if you go to the store and you buy a 6-pack, all right, that's 6 cans or bottles per 6-pack of your beverage du jour. 21 and over, maybe it's beer, 19 in Canada, but everybody else, hopefully Coca-Cola, something like that. But anyway, I digress. The counting unit is really important. When you go to the donut shop, you usually get a dozen donuts, where a dozen is 12, all right? Well, in chemistry, the counting unit is called the mole. And this little guy, who looks like the little dude that runs around your grass and makes holes and stuff like that, if that's a problem you have, the mole is actually the name of the counting unit. It's not the little creature that does that thing to your grass. A mole is kind of like a dozen, all right? If you're going to buy your significant other some roses, you might buy them a dozen roses, 12, all right? The mole is kind of like that, but instead of a number 12, which is manageable, the number is really, really big, all right? We'll talk about that in a little bit. So you could say to your significant other, oh, I'm going to buy you a mole of roses, but oh man, you'll see how many roses that is. It's a massive, massive number. Kind of cool. This guy, Oswald, was the first one to come up with the idea of the mole. And it's kind of an interesting story. He really didn't like the idea of having moles moles and counting units, but it ended up working out. That's the way it happened. But anyway, he's kind of a cool looking dude. Show his picture. Avogadro is really more of a mathematician. And look at the dates there. Around the time, the early 1800s or so, is when he discovered, he proposed the idea that a number exists for a counting unit. And there's a lot of cool history that goes into this, but long story short, he proposed the number, and scientists later actually came up with it. And the number is this number right here, 6.022, a whole bunch of numbers, times 10 to the 23rd. So it's a number which is definitely based in significant figures. All right, this is a lot of significant figures as listed. The number does change every once in a while, and several times since I've been teaching, the number has changed. But this is the number of pieces in a mole. So, for example, if we're going to talk about copper atoms, and you had a mole of copper atoms, you would have 6.022 times 10 to the 23rd copper atoms in a mole of copper. So if I handed you a mole of copper, you'd know that was 6.022 times 10 to the 23rd. You can also have a mole of carbon dioxide molecules, no problem. And again, a mole of anything, 6.022 times 10 to the 23rd. So if you have a mole of carbon dioxide, you would have 6.022 times 10 to the 23rd of them. If you had a mole of roses, you would have 6.022 times 10 to the 23rd roses. So again, you can hopefully see how this is just like a dozen, all right? It's the same kind of thing. It's a counting unit. But while a dozen is a number that kind of makes sense in our world, this 10 to the 23rd, freaking large. So let's talk about how big a mole is. How big is that 6.022 times 10 to the 23rd? And these are just some kind of interesting things. So let's say that we had a stack of 6 times 10 to the 23rd pennies. It would be so tall that it would take 100,000 years traveling at the speed of light to go from one side of the stack to the other. So, whoa, I like science fiction a lot, and that's just like a crazy amount of time. So this is a lot of pennies, all right? You don't really necessarily want to have 6.022 times 10 to the 23rd pennies. It would be pretty big. It would take more than 100 trillion years to print 6 times 10 to the 23rd dollars if you can print at $100 a second. And that's pretty massive speed right there. But this 6 times 10 to the 23rd is so large, it would take forever. So it would take just incredible amounts of time just to print the dollar bills. If you traveled at the speed of light, it would take more than 100 billion years to travel 6 times 10 to the 23rd miles. So again, just a massive distance. And that's assuming that you're going the speed of light, which is huge, 2.998 times 10 to the 8th meters per second. And let's say that you had 6 times 10 to the 23rd dollars, and you wanted to be cool and give and spread them out to all the human beings on the planet. And then you want them to spend $1 million an hour. It would take more than 10,000 years just to spend your share, all right? It's, again, this number, the goal of all of this is, first of all, just to go, whoa, I guess. But anyway, the goal is just to show you this is a massive number, all right? Powers of 10, if we go back to them, remember 10 to the 3rd was 1,000, and 10 to the 6th is 1,000,000. 10 to the 9th would be 1,000,000,000. So the 10 to the 23rd number is more than 1 billion, all right? It's just massive. So this is a big number. A mole of carbon-12, pure carbon-12. Remember that little superscript is the mass number. So this is pure isotope of carbon-12. It's been defined then as if you have exactly 12.00 grams, that's what a mole is equal to. And they've done some measurements on it to figure that out. Well, if we have a mole of something, that means we also have 6.022 times 10 to the 23rd atoms of carbon. So notice here the connection. We can measure 12.00 grams in the laboratory. There's no way we could count 6.022 times 10 to the 23rd atoms, but we can manipulate these massive amounts of atoms through measurements which make sense in our world. So this kind of relationship, grams to moles to atoms, is pretty important for chemists. They call the 12.00 grams of carbon-12 the molar mass. It's the grams of carbon in a mole of the compound. And remember, if you have a mole, you've got 6.022 times 10 to the 23rd atoms. Most of the time, carbon is a mixture of isotopes. There's carbon-12, a little carbon-13, and 14. So if you look on the periodic table, hint, hint, 12.011, that number down there, that is the molar mass of carbon with all the isotopes. And this is exciting because if you weigh out 12.011 grams of carbon, you're going to have 1 mole of carbon. And again, 1 mole is 6.022 times 10 to the 23rd. So the numbers here are going to be really important to us. I couldn't even wait until this slide. I gave it away. That number on the periodic table, the atomic weight we saw in an earlier chapter, was represented the average mass of one atom. So one average aluminum atom would be 26.9815 AMUs. But there's a second reason for it. All of those numbers have been calibrated so that they also are the molar mass of those elements. So 26.9815 also represents the grams of aluminum in a mole of aluminum, and it does take into account all the isotopes of aluminum, which is really cool. So hardly anybody honestly uses the average mass of one atom. That's kind of a weird esoteric thing. But oh my goodness, to know the molar mass of the elements, that's where things start to really get happening. So those numbers on the periodic table, look at your own periodic table right now. They represent the grams of those elements in a mole of the element. And if you have that many grams, that means you've got 6.022 times 10 to the 23rd atoms. So here's the periodic table, just showing some more examples of how this works out. So here's like silver, Ag, here's carbon, we talked about earlier, and there's sulfur. So those numbers that are on the periodic table, to more or less sig figs, those are the molar masses. So silver is about 107.9 grams of silver in a mole. If you have about 107.9 grams of silver, you have a mole of silver. And that's again 6.022 times 10 to the 23rd. Sulfur, it takes 32.07 grams of sulfur to make a mole, but the same idea. All of those numbers are the molar masses. So this is another way that the periodic table really helps chemists out. Here's actual mole amounts, and you can see there the different densities which affect it. So sulfur is got a lot of density, magnesium too. It doesn't look like you have a lot of silicon or copper, but that's because their density is great. But either way, those numbers that I have there, 63.5 for copper or 32.1 grams for sulfur, those literally are the molar masses on the periodic table. All right, sulfur was 32.07. If you round it up to a tenth, that would be 32.1. But with that one little nuance aside, you can see it. So those amounts of those 5 elements, those are mole amounts. So in those quantities, you've got 6.022 times 10 to the 23rd. So when you look at that amount of copper right there, that's 6.022 times 10 to the 23rd atoms of copper. And the same for sulfur and magnesium and tin and silicon. Let's say that we have 0.200 grams of magnesium, and we're curious how many atoms are inside there. Now, 0.200 grams is not a lot. It would fit on your pinky, all right? It's not a very large amount. But we can do this kind of calculation using the molar mass and Avogadro's. We're going to go grams to moles to atoms, or some combination like that, a lot here. And in order to do that, you've got to look on the periodic table and look up the molar mass. So magnesium is 24.3050 grams per mole. So using then dimensional analysis, we're going to start with our 0.200 grams. Most of the time, instead of using all the sig figs, you can use it just to the hundredth. So notice notice that 24.3050, I rounded up to the 100th. The first number to be dropped is between 5 and 9, so 24.30 becomes 24.31. And that again is the molar mass. You want grams to cancel out, so grams on the top cancels grams on the bottom. You want the answer to be 3 significant figures. That comes out to be 8.23 times 10 to the minus 3 moles. And again, if your number came out 0.00823, it might be a good idea to know how to go back and forth between scientific notation and regular decimals. And these kind is going to be neat. Now, that mole number really isn't that impressive. I don't even know what that means, honestly, myself, after being in chemistry all this time. However, if you want to know how many atoms were in that 0.200 gram sample, that's where it gets exciting. Now, to figure out atoms, you must know the moles. You can't go directly from grams to atoms. You've got to have the mole bridge in between the two. And that's where 6.022 times 10 to the 23rd comes in, because for this problem, that would represent atoms of magnesium per mole. So just like on the last one, we'll start with the moles, our starting unit. We're going to use Avogadro's number, which is that 6.022 times 10 to the 23rd. We want our moles to cancel because we want to end up with just atoms. 3 sig figs, because 8.23 is only 3 sig figs. When you put this in your calculator, 4.96 times 10 to the 21st. And remember, 10 to the 9th is a billion, so 10 to the 18th would be a billion billion. This is more than a billion billion atoms of magnesium in your really small 0.200 gram sample. That amount of magnesium would literally fit on your pinky, and that has 10 to the 21st atoms inside it. Process that. It's kind of cool to think about how many atoms we consume and use in a day-to-day kind of basis. Atomic weight, all right, is what we talked about that number was earlier, and that was the mass of an average atom. And that's a cool thing too, all right? And it takes into account all the isotopes, blah, blah, blah. However, it also has, of course, the molar mass thing, which is neat. Now, a periodic table always shows atomic number and, quote unquote, the atomic weight. All right, if it's a good one anyway, let's put it that way. All right, and that's fine. That's totally cool. However, atomic weight and molar mass, which is what we just talked about, it's the same number but different units. The way they arranged the average mass of copper 12 versus the molar mass of carbon 12, how they figured out the average mass of a carbon 12 atom and the molar mass of carbon 12, it was the same thing. So what this means for you and me is that 26.9815, that has two meanings. It can represent the average mass of one atom of aluminum, which is kind of interesting, but more importantly, it also represents the molar mass. How many grams are in a mole of aluminum? So if you have 26.9815 grams of aluminum, you've got a mole of aluminum, and a mole of anything 6.022 times 10 to the 23rd. But it also does represent the AMU, the average atomic mass units of the average aluminum atom. And so both have their use. The molar mass is by far more useful, so we'll use that a lot more than the other one. The molecular weight is just the sum of atomic weights for all the atoms in a molecule. And again, molecular weight we can represent as molar mass if you want to. And let's have a periodic table. If you don't have a periodic table, make sure that you get one. Pause the video, go get a periodic table, and come back. Okay, assuming you have a molar periodic table in front of you, let's say that you wanted to know what carbon was. All right, well, on the periodic table, carbon is 12.01 AMU. That's the atomic weight of carbon. Oxygen is 16.00, the atomic weight of oxygen. But here's kind of the cool part. Let's say you wanted to know the atomic weight of carbon monoxide, which is CO, all right? Well, then what you would do is you would add the carbon and the oxygen together. So 12.01 plus 16.00 is 28.01. And 28.01 AMUs is the molecular weight of a carbon monoxide molecule. And that is kind of interesting. However, 28.01 has two meanings. It's also the molar mass of carbon monoxide. And all we're going to do is just change AMUs to grams per mole. So carbon monoxide, 28.01 grams per mole. If you have 28.01 grams of carbon monoxide, you have a mole, which means you have 6.022 times 10 to the 23rd. So do realize that, first of all, a couple of things. Molecular weight, molar mass, same number, different units. You just take off one unit, put the other one on, and you're good to go. However, if you want to find the molar mass or molecular weight of a compound, you just add up the individual atoms together like we did here for carbon monoxide. And this is really cool too. We're not limited to just the elements. We can also do the compounds as well. Let's find the molar mass of water. And if you want to find molecular weight instead, that's fine. But let's talk about molar mass. Now, water has 2 hydrogens and 1 oxygen. All right. So we're going to take the molar mass or atomic weight of 2 hydrogens and add them to 1 oxygen. So if you look on the periodic table, hydrogen is 1.008, and there's 2 of them. So this many grams comes from the hydrogen. And oxygen, 15.999, 1 times that number is this number right here. And you add them together, the molar mass, 18.015 grams per mole. That's the molar mass of water. So if you have 18.015 grams of water, you have a mole of water. And a mole of anything, 6.022 times 10 to the 23rd, that would be the number of molecules of water in 18.015 grams. Pretty cool. So in 18.015 grams of water, you've got 1 mole. You have a mole of molecules of water. And again, that would be 6.022 times 10 to the 23rd. Oh, yeah. That 18.0, 18.02, 18.015, depending on how many sig figs you want to use, that's a conversion unit. That allows you to go between grams and moles of a compound. So let's say you had 0.25 moles of water and you were curious how many grams that is. No problem. Start with the moles, set up the conversion unit so that moles are on the bottom so they cancel. You're only going to have grams left over. That would be 4.5 grams. No problem. On the other hand, if you wanted to go from grams to moles, like all conversion factors, you can flip them. So in this case, 27 grams to moles, you'd have grams on the bottom, canceling grams on the top. Moles is the only thing left. 27 divided by 18.0 to 2 sig figs, 1.5 moles. So again, remember conversion factors, you can flip back and forth like 4 quarters per dollar or $1 per 4 quarters. And this is the same thing with molar mass, which is a really neat kind of concept. Let's figure out the molar mass of urea. Now, urea is NH2 parentheses 2 CO. It's a compound that's used in organic chemistry sometimes. No problem. We're going to need a periodic table. Now, urea has 2 NH2s. So that means 2 nitrogens, and 2 times 2, 4 hydrogens, plus the C and the O. So if you do this on the periodic table, here's the 2 nitrogens. Nitrogen to a bunch of sig figs, 14.0067. So that would be the grams for the nitrogen. Here's the 1 carbon, about 12.01. The 4 hydrogens, 4 times that number, and don't forget the oxygen. So what you would do is you would add these numbers up on the far right. That'll give you the molar mass of urea. Total 60.0556 grams per mole. That's the molar mass of urea. So if you have about 60 grams of urea, you're going to have 6.022 times 10 to the 23rd molecules running around. Now, I do not usually use that many sig figs when I'm doing a molar mass. Usually what I do is I would cut it off at the hundredths, or 2 positions to the right of the decimal. And 99% of the time in chemistry, if you cut it off at the hundredths, that'll give you all the significant figures you need. However, it is nice if you have the time or the mathematical power to figure this out, and that's why I showed you the whole example. I'd also like to give a small advertisement. You can get a molar mass calculator, either online or an app for your phone. Both Android and iPhones have several of them, and it can be super helpful in this section. Also on the computer, you can look up molar mass calculator online or something, and free ones will pop out. But they can be really, really handy. I want you to know how those numbers came around, like here, but also in the future when you've got some wild molecule and you don't really feel like doing this process like we did for urea, the molar mass calculator can be nice. But again, try to at least go to 100th of a gram per mole if you can, and you'll be good to go. You don't have to use this many sig figs. Let's figure out the molar mass of another compound, potassium dichromate, which is kind of a funky yellow color, by the way. All right, no problem. Potassium dichromate has 2 Ks, 2 potassiums, 2 chromiums, and 7 oxygens. All right, so if you look up these things on the periodic table, which you have to have, this one is the 2 potassiums, 2 chromiums, 7 oxygens. These I only went to the tens, hundreds to the thousandths. So even though the potassium went out farther, we cut it off here. Got to cut it off at the largest doubtful digit. So because the CR and the O stopped at the thousandth, our final answer stops at the thousandth as well. But again, if this was a real life situation, if you only go to the hundredth, 2 positions to the right of the decimal, honestly, that's fine. 99% of the time. Now, let's say we have 35.013 grams of potassium dichromate, and we're curious how many moles we've got. All right, we can use that number we just calculated to do it. Now, down here in the bottom, you can see there's a thing of mass in grams, and then in the top part is moles. That's where we're going to go from mass, lower left, to moles in the top. Sometimes they call this the molar bridge. And in order to do that, we need that molar mass. We have to turn the grams into moles. And again, this is just good old dimensional analysis. We're starting with grams. We're going to use that grams per mole on the last page. We're going to have the grams part on the bottom and moles on the top, so the grams cancel out. So if you do that, here's the molar mass from the last page, 294.185. Grams on the top cancels grams on the bottom. Moles is the only thing left over. This has got a lot of sig figs in it, but 5 sig figs, 0.11902 moles potassium dichromate. So you can see how the molar mass allows you to go from the mass of an object to the moles with no problem. Molar mass is cool to allow you to go from grams to moles, but if you need to figure out how many molecules of something there is, then you've got to use Avogadro's number. So before we went from mass in grams to moles, now we're going to go from moles to number of molecules. They put particles there because you could have atoms and you could have molecules and you could have ions or a whole bunch of different things. But either way, the punchline is we expect a large number. All right, so we're going to multiply by Avogadro's number. We're going to take the moles from the part 2 answer and essentially multiply it by the Avogadro's number. The grams are the same, so you could go grams to moles using molar mass and then moles to molecules, or you could just start with the last example. Anytime you have molecules or atoms, that's where Avogadro's pops in. And Avogadro's pops in when you have 1 mole of that compound, all right? So you can think about this as 1 mole K2Cr2O7 per 6.022 times 10 to the 23rd molecules of potassium dichromate. Mathematically, what it looks like, If you want to start at the beginning, 35.013 grams, we're first going to divide by grams to get to moles. And this conversion right here, again, is the molar mass we talked about. Grams on the top cancels grams on the bottom. This is the moles. That would be the answer we had in the last slide. But now we're going to use Avogadro's number. And that's always a big number of molecules per 1 mole. All right, could be atoms, could be something else, but in this case it's molecules. You want to have moles on the top and moles on the bottom so they cancel. So then you've got molecules. And to 4 sig figs, because that's the sig fig number we use for Avogadro's number, 7.167 times 10 to the 22nd molecules of potassium dichromate. So again, a massive number of molecules in a relatively small number of grams. Percent composition is another tool of the trade you can use. Percent composition is usually referred to as percent by mass. And the reason for that is you could have a percent by volume, like 1 milliliter of Diet Coke and 3 milliliters of Diet Pepsi. That would be like a volume percent. That's really nerdy. But anyway, percent by mass, aka percent composition, aka percent by weight, although that's weird too, as we talked about earlier. Anyway, that's a useful thing for chemists. It tells, like in water, what percentage of water is hydrogen and what percentage of water is oxygen, stuff like that. Let's say we have a new compound. It has 55 grams of X and 45 grams of Y. And if we have 100 grams from it, I wonder what the percent composition would be. No problem. It's almost always mass of everything on the bottom and mass of what you're looking for on the top times 100%. All right. So in this case, if you were curious as to the percent of X, you would have 55 grams of X on the top divided by 100 grams total times 100%, 55% X. And you could do the same thing for Y. You'd have on the top, you'd have grams of what you're looking for, which is the Y, 45 grams. Grams of everything on the bottom, 100 times 100%, 45% Y. Now, all the percentages together should be equal to 100 or very, very, very close. And so in this case, you can see it's 55 plus 45, which is 100%. That's good. That's a nice way to kind of check yourself when it comes to these. So again, this works for all compounds. You can find percent carbon or percent lithium or whatever. You take the grams of what you're looking for example, lithium, and you divide it by the grams of everything on the bottom times 100%. You can get a percent composition from the chemical formula. And this is kind of a cool thing. So what you need to do if you want to do this is you first got to find the molar mass of the compound itself. And along the way, you're going to find the molar mass of the elements. And if you assume that your sample size is just 1 mole, all right, you can use that molar mass to figure this out. And it's kind of clever. So you want to take the mass of just the element and divide by the molar mass of the compound times 100%. So for example, for water, water is about 18 grams per mole. The 18 number would go on the bottom. Now, if you were looking for percent hydrogen, the element hydrogen would go on the top. There are 2 hydrogens, and each hydrogen is about 1 gram per mole. So percent hydrogen in water would be 2 times 1, representing the grams of hydrogen, divided by 18, the molar mass of everything, times 100%. It's pretty clever. It's kind of weird to talk about, but in practice, it's pretty easy to calculate. Let's do the actual percent composition of water, and let's see what I was babbling about earlier. All right, so first of all, you do need the whole molar mass, and as we've seen, that's about 18.02 grams to 100th anyway. And the 18.02 came from 2 hydrogens, 2 times 1.01, which is 2.02 grams, and the 1 oxygen, which is this number right here. And if you add those together, it's about 18.02. The oxygen is actually 15.999, so it rounds up to 18.02. Sorry about that, that's a little confusing. But anyway, 18.02 is the molar mass of water. So the percent of hydrogen, if you want to figure it out, and you know the formula, molar mass in the bottom, 18.02, and the grams of hydrogen in the top. So grams of what you're looking for, hydrogen, divided by grams of everything, which is the molar mass times 100%. Water is about 11.2% hydrogen, and that's kind of a cool thing to know. Now, for oxygen, it would be very similar. Oxygen, 88.8% oxygen. So water is about 11.2% hydrogen, about 88.8% oxygen. If you add those together, it's about 100%, which is good. Woohoo! This is how you can figure it out. So you can figure out sodium and sodium chloride, or oxygen and ethanol, or whatever you want. Molar mass on the bottom and grams of just the element you're looking at on the top. Let's find the percent composition, or percent by mass, for sodium hydrogen carbonate. And what this means is we want to find the percent of all the elements. Now, sodium hydrogen carbonate is NaHCO3. So there's 4 elements, NaHCNO. And the first thing we got to do, find the molar mass. So I did that part here for you. I added up the sodium, the hydrogen, the carbon, and the oxygen. And when you add those together, 83.98 is the molar mass. Now, when we do these percent composition, that 83.98, that's going to be in the bottom all the time. And we'll put 22.99 in the top if it's percent sodium. If it's percent carbon, we would put 12.01 in the top and 83.98 in the bottom, etc., etc. So here's the actual process. Here's the sodium, 22.99 divided by molar mass times 100, 27.38. And hydrogen, because there's one of them, 1.01 divided by that. Sig fig's a little bit different. Carbon, oxygen. And again, if you've done this right, when you add them together, they should be very, 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 very close to 100%. And they are. So pat yourself on the back. Nice job. Little things make my day. This leads us to the next and final topic of this section, which is what they call the empirical formula, molecular formula. And the molecular formula is kind of like a holy grail for chemists. As I said at the beginning of this lecture, chemists a lot of times are paid for identifying compounds when it's not known. So you go pick up some sludge at your grandfather's house. What's in the sludge? I don't know, but the chemist can figure this out, all right? And it's kind of a wild process. But in order for the chemist to tell you what it is, they first have to find the empirical formula. So notice the abbreviations, all right? We're going to use EF for empirical formula and MF for molecular formula. But before we talk about how to do these, we need to talk about what the heck EF and MF actually represents. So the molecular formula is the actual formula of the compound, and it represents the number of atoms, all that kind of stuff. The empirical formula is the lowest whole number ratio of atoms in a compound. And if that's as clear as mud, I completely understand. Let's look at some examples. C6H6 is a compound that's used a lot in organic chemistry. It's called benzene, and the molecule benzene does have 6 carbons and 6 hydrogens. If you want to define the empirical formula for it, it's the smallest or lowest whole number ratio. So notice that if you take CH and you multiply it by 6, that's going to give you the actual formula for benzene, C6H6. So for benzene, we would say that the molecular formula, C6H6, but the empirical formula, the smallest whole number ratio of atoms, just CH. The formulas for ionic compounds are always the empirical formula. That's a nice thing about ionic compounds, but it's mostly the covalent ones which we have to worry about. These are all examples of ionic compounds, and they're always the empirical smallest whole number ratio. NaCl, MgCl2, K2CO3, which have polyatomics, etc. Notice here there's no like Mg 1/2 Cls. Chemists usually don't like like fractions. So don't do anything with fractions if you can help it. These are smallest whole number ratios. It makes everything a little bit easier. However, for the molecular compounds, the covalent nonmetal plus nonmetal compounds, they might be empirical, they may or they might not. Here's some examples of different things that I happen to think of. Water is the molecular formula. It's H2O. And you can't make H2O any smaller without going into those dreaded fractions. So water has the same empirical and molecular formula. You can't break water H2O down any farther. However, C6H12O6 is a type of a sugar, and this one now does have an empirical formula. If you pull 6 out of the CH and O, you can see you'd be left with 1 C, 1 O, and 2 H's. We would say that CH2O is the empirical formula of C6H12O6. Again, it's the smallest whole number ratio of atoms in a molecule. However, C12H22O11 is another type of a sugar, and you can't break this one down into smaller numbers without getting into fractions. So the empirical and the molecular formula for this one are like water. It's the same thing. So some molecules have different empirical formulas, molecular formulas, and some of them have the same. It happens both ways. Here's some more examples. N2O has the same empirical and molecular formula, but C2H4O2, if you divide all of those by 2, you're going to get CH2O. So this one has a different empirical molecular formula. And you can see the next two you can break down to smaller ones. C2H6O2 becomes CH3O, and N2O4 just NO2. So it's cool to know how to go from molecular formula to empirical formula, see if they're any different. If you go from empirical formula to molecular formula, you have to know what to multiply. So for example, CH2O, you would multiply by 2. All right, NO2, you'd multiply by 2. But N2O's empirical formula, you would multiply by 1. And these numbers, whatever they are, 1, 2, 3, or 4 even sometimes, always whole numbers, no fractions, and that's going to be important to us later on. So if you're going from empirical to molecular formula, you always scale up using a whole number. It's never a fraction. You can find the empirical formula from mass percentages, and that's why we're studying both of these two things right now. And it's kind of a cool concept. If you're going from a mass percentage to an empirical formula, there's some rules that will help you out. First of all, always assume 100 grams total, because whatever your percentages are, those will represent the grams of those elements. And once you do that, you want to take those grams and turn them into moles. So if you have 37% hydrogen, that would be 37 grams of hydrogen. And if you have 37 grams of hydrogen, you can turn that into moles using the molar mass on the periodic table. So grams, percentages to grams, grams to moles. And then finally, you want to compare the moles and find the smallest value of the moles and divide all of them by that. And that'll make more sense when we go through it. But let's say you had 2 moles of carbon and 1 mole of hydrogen. You would want to divide by 1 mole, the smaller of the numbers. And the ratio you're going to get then is going to be very close to the empirical formula. Now, if you end up with a fraction like 1.33 or 2.5, you might have to multiply this step by 2 or 3 or something to make it whole. But the goal is, at the end of step 4, is to find the empirical formula, which is a small whole number ratio of atoms. Let's see some examples, because I know this is a little weird to talk about. Here's a problem. 40.05% sulfur, 59.95% oxygen. We know it's some kind of sulfur oxide, but what is the empirical formula? How do we turn those percentages into an empirical formula? And that's really cool. So again, like we talked about, first thing, go percentages to grams. And if you have 100 grams, that makes this really easy, because that would be 40.05 grams of sulfur and 59.95 59.95 grams of oxygen. So here's the percent of sulfur. Assume 100 grams, 40.05 grams. And once you do that, you can use the molar mass, which again comes from the periodic table. So sulfur, 32.07 grams per mole. You can turn those grams of sulfur into moles of sulfur. So percentages to grams, grams to moles. And we're going to do the same thing now for the oxygen. So 59.95% oxygen becomes 59.95 grams of oxygen. And we can divide that by the molar mass of oxygen, get 3.749 moles of oxygen. So now we've got the moles of sulfur and the moles of oxygen. And at this point, we could write S 1.2490 3.749, and that is a type of a formula, but man, is that ugly. All right, all the formulas we looked at in the last section were like SO2, SO3 or something like that. There's no S 1.2490 3.749. That's really, really ugly. So we need to clean the formula up, and that's where dividing both of those moles by the smaller number comes in really handy. So 1.249 was smaller than 3.749, so we're going to divide both of the moles by the smaller one. And 1.249 divided by 1.249 is exactly 1. That's easy. In your calculator, 3.749 divided by 1.249 comes out to be almost exactly 3. 3 oxygens per 1 sulfur. That's a formula. SO3 is the empirical formula of this compound. So again, we took the percentages and turned them into grams, and that's easy because assume 100 grams. Then we turned those grams of the element into moles to get these two numbers right here. We divided both numbers by the smaller, 1.249 in this case. The one was automatically equal to 1. The other one turned out to be 3, SO3. In this example that we just did, it was a nice whole number. 1 sulfur to every 3 oxygens, empirical formula SO3. All right. Sometimes you'll have like a 1 to 2.5, all right, ratio. And again, you don't want to have fractions at this level. You want whole numbers. So if you have like a 1 to 2.5, you need to think about how to make the 2.5 a whole number. And if you would multiply 2.5 by 2, that would give you 5, and that's a whole number. But if you do it to one atom, you do it to the other atom. So you'd have to multiply the 1 by 2 as well. You would have had like S2O5 or something like that in that case. So be careful. This part can be a little tricky. And in Chem 151, it won't be as crazy as other classes, but just think about it. You always want to have whole numbers. Here's another example. Butene is what they call a hydrocarbon, which is a compound with carbon and hydrogen. Once in a while they throw oxygen in, but that's another story. Anyway, butene is 85.63% carbon and 14.37% hydrogen. Let's find the empirical formula. And again, what we're going to do, we're going to take these percentages, turn them automatically into grams, and then grams to moles. So we'll end up with moles of hydrogen and moles of carbon. So in 100 grams, we'd have 85.63 grams of carbon and 14.37 grams of hydrogen. We'll use the molar mass on the periodic table. Those are both the molar masses of those two elements. And we're going to end up with 7.130 moles of carbon and 14.26 moles of hydrogen. And this right now is, as I said earlier, kind of a formula. It's C7.130H 14.26. But again, that's a super ugly formula. So we need to clean it up. And that's where dividing both of them by the smaller one is what we want to do. So 7.130 is smaller than 14.26. We're going to divide both of them by that number. And you can see that you get definitely 1 mole of C, and you end up with 2 moles of hydrogen. 2 to 1 is like C1H2, empirical formula CH2. having the empirical formula is cool, but it may not be the final answer. And we saw some examples earlier where empirical formulas and molecular formulas were the same, but we also saw some when they were different. So for example, NO2 and N2O4 would be the same empirical formula. NO2 is a compound. It's a pollutant. It's kind of funky. It's also a clear gas. N2O4 is a heavier gas with a brown color, not quite as bad, but they're both separate compounds. They will have the same empirical formula, but they're different. And the same thing if C2H4, which is called ethene, it helps keep our bananas ripe, and C4H8 butene, which is a type of a fuel. They both have the same empirical formula, but they're different compounds as well. So sometimes knowing the empirical formula just isn't enough. We need to go that extra step. And we go that extra step because if, let's say, you found an empirical formula of NO2, you still wouldn't know if it was NO2 the pollutant or N2O4 the brown gas. You've got to know more about it. So that's where the molecular formula is helpful. The molecular formula allows you to know if you have NO2 or N2O4 or C2H4 or C4H8. Without knowing that, you wouldn't know which of the compounds you have. Empirical formula is only the smallest thing. So really what that means is that the percent nitrogen and percent oxygen in NO2 and N2O4 are the same. Again, it's going to come down to more than just the mass percentages or the empirical formula. You've got to know more. So that's why molecular formula is kind of a holy grail. C2H4 and C4H8 would have the same percentages by mass, same percent carbon, same percent hydrogen. They have the same empirical formula, but they're different compounds. So this is where the molecular formula is really helpful. The molecular formula represents the actual number of atoms. So that's why N2O4 would be different than NO2. All right, N2O4 is heavier, etc., etc. You need the molar mass of your compound to find the molecular formula. And there's something called a mass spectrometer. And a mass spectrometer is actually fairly common in chemistry. It's a way to find the molar mass of your compound. So when you have a compound and you only know the empirical formula, if you throw your compound in the mass spectrometer, you'll get a molar mass value. And you can use the empirical formula and the molar mass to find the molecular formula. Let's see an example of how this works out. So here's a compound. It has a molar mass from the mass spectrometer, a molar mass of 181.50 grams per mole, and the empirical formula C2HCl. Let's use this information to find the molecular formula of the compound. No problem. What you need to do is first you need to find the molar mass of the empirical formula. So the empirical formula was given to us here, C2HCl. So if you add up 2 carbons, 1 hydrogen, and 1 Cl, you would have 2 times 12.01 for carbon, 1 times 1.01 for hydrogen, and 1 times 35.45 for chlorine. 60.48 is the molar mass of the empirical formula. And this number, you can see, is quite a bit different than the molar mass of the whole compound. So if you compare the molar mass of the whole compound to the molar mass of the empirical formula, you should end up with a whole number. And it's always going to be a whole number here. So in this case, 181.50 divided by 60.48, 3.001, that's awfully close to 3. So that's the whole number we're looking at. And to find the molecular formula, we're going to take that empirical formula and multiply it by 3. So in this problem, C2HCl taken 3 times means that the molecular formula C6H3Cl3. So let's backtrack. We need the molar mass of the whole compound, And if we find the molar mass of the empirical formula, which is what we did right there, you can compare the molar mass of the whole compound to the molar mass of the empirical formula. And you should always get a whole number. And that whole number, you multiply it by the empirical formula to get that desired molecular formula. So C6H3Cl3 would be like the holy grail here. Pat yourselves on the back. Chemistry world, that's pretty cool. Here's an example of a problem you might see. And this is the whole shebang for this chapter. We're given the percentages by mass in the compound, and we're giving a molar mass for the compound. And what we want to do here is we want to find both the empirical and the molecular formula for this compound. No problem. We're going to combine the steps we just did and figure this out. So the first step will be to find empirical. We'll take the percentages, turn them into grams if we have 100 grams, and then find moles, compare them to find the empirical formula. Then we'll take the empirical formula's molar mass, compare it to the 146, and we'll be able to find the molecular formula that way. So we're going to assume 100 grams, all right? So the percentages will equal the grams of the element. We'll then turn those grams into moles. And from the moles, we can compare the moles. We'll divide the moles by the smaller number. That's going to lead us to the empirical formula. And after we have the empirical formula, we're going to find the molar mass of the empirical formula and compare it to the 146 number. It's always going to be a whole ratio. That whole ratio will multiply by the empirical formula to find the molecular formula. There's all the information, but in a smaller font. But if you need to look back on it, you can. First thing, percentages to grams to moles. So all those percentages, we're just going to turn directly into grams. So 49.32% would be 49.32 grams of carbon, etc., etc. Then the next part, grams to moles. So on the periodic table, carbon is 12.01 grams per mole, hydrogen to the 100th 1.01 grams per mole, carbon 16 grams per mole. So then we've got these numbers right here, the carbon, hydrogen, and oxygen. And the next step, we want to take the smallest number, 2.740, and we're going to divide all of those numbers by 2.740 and see what pops out. Now in this case, all right, here's the carbon, 4.107, dividing it by the 2.740. Notice how we get 1.5. 1.499 is like 1.5. And something like that happens with hydrogen too. You get 2.47, which is like 2.5 if you round up, and 1 oxygen. So this is an example of having an empirical formula with not quite whole numbers. And you've got to have a whole number when it comes to the empirical formula. So in this case, if you think about it a little bit, we can multiply all of that by 2. 1.5 times 2 would be 3, 2.5 times 2 would be 5, and of course 1 times 2 would be 2. So if you do that, you end up with an empirical formula of C3H5O2. Remember, don't leave anything in fractions. Chemists don't like fractions. That'll help take care of business here. So C3H5O2 is our empirical formula, and that's a great first step. But we're not sure if that's the final answer or not. Our final answer could be C3H5O2, or it could be twice that. It could be C6H10O4 or C9H15O6. Any of these kind of things are possible. So this next step, we'll take the empirical formula and turn it into a molecular formula. And we're going to do that by figuring out the molar mass of the empirical formula. So C3H5O2 is what we figured out on the last slide. Let's find the molar mass. So 3 carbons, 5 hydrogens, 2 oxygens, and there's the individual molar masses. This number comes out to be about 73 grams per mole. That's the molar mass of your empirical formula. And we can compare that to the molar mass of the whole thing, 146. Now these ratios will always be whole numbers. And in this time, it comes out to be 2.00, which is pretty awesome. If you don't see a whole number here at this level, you probably have done something wrong. In the empirical formula part, you can get into weird fractions, but here the ratio should always be a whole number. So because the ratio is 2, twice the empirical formula, or 2 times C3H5O2, that's going to be our molecular formula. And this molecular formula for this problem, C6H10O4, that's the molecular formula. I encourage you to practice this process. There's several examples online that you can look at on our website and on other websites. It's not a difficult process, but as long as you go through the steps, you should be pretty good to go. Here's another example. This one I do want you to do by yourself. This is as a liquid. It's a nitrogen-oxygen compound. 46.68% nitrogen, 53.32% oxygen. And the molar mass of the whole thing, 60.01. What's the molecular formula? And along the way, you're going to need the empirical formula. Now, I'm going to let you figure this one out on your own. But if you've done it correctly, the empirical formula comes out to be NO, 1 nitrogen and 1 oxygen, and the molecular formula N2O2. If you don't get these numbers, you let me know and we'll go through it. If you would send me a screenshot of the work you've done so far via email, I can look it over and try and figure out what's going on. But if you did get it, pat yourself on the back. This is cool. Okay, that's it for Chapter 2, Section 2.4's lecture. You can see how a chemical formula has a lot of information that people don't usually think about right away. If you have questions on this or anything else, please let me know. I'm happy to talk about it with you. You can email me. You can also talk to the Learning Success / Avid Center on campus. They'll help you. There's ways to get assistance here. You don't have to do this by yourself. Good luck with your studying. I'm rooting for you and have a great day.